Okay, today it's going to kind of feel like we don't do any calculus. Okay? So we've been talking about antiderivatives. Okay? We're going to now talk about sigma notation. And eventually we're going to bring our antiderivatives together with what we talk about today and next week and how they actually relate to each other. So right now it's going to feel very separate, but eventually these two concepts will come together, okay? So you've seen this before, the Greek letter sigma. It means add everything up, right? We worked with sequences and series in pre-calculus, right? Seen it before? Thank you.
It's been a while. Is that green?
Second tomorrow.
No, it's Sunday.
Sunday. All right, so let's remember all of our notation. Okay? You're going to have the sum of a function from a value to a value, okay? So the sigma means you have a sum. This here tells you what number to start with, and whatever the variable is, in this case, k, we're going to plug those numbers into k. You will start by plugging in m. You will end when you get to n, and you will add up all of the terms. In this section, we are always going to use k in here. Okay, so this is going to be some function in terms of k. So then this is going to be a k. These are going to be numeric values. Eventually, we're going to get to the point where this top number is not a numeric value. But that'll be sometime next week, I think, or the week after. But we'll start here, we stop here, we're going to add up all the terms. For example, if we have, go and write this one down right here. The sum from k equals 1 to 5 of k squared. This means we start at 1, we end at 5, and we substitute in all of the integers in between. Okay? So we're going to plug in 1, and then 2, and then 3, and then 4, and then we stop when we get to 5. Okay? So the sum from k equals 1 to 5 of k squared is 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared.
55.
Are you confident on that? I didn't add it up before. Okay. We plug in 1, we plug in all the integers in between until we get to 5. So then here we have the sum of k equals 3 to 8 of 7. Mrs. Holman, there is not a k for us to plug into. Is that a problem?
Yes. No.
When we plug in 3, what do we get for our value? 7. When we plug in 4, 5, 6, 7, 8. How many is that?
Well, 5, 4, 5, 6. Oh, you're asking for the sum.
All right, so let's do some examples. We will start off easy. I'll have you do this one. The sum from 3 to 8 of 2k. Carter, what do you have?
66.
Do you agree with 66? Yeah? Next sum. This might be the only one that doesn't have a K. It has an I instead, but that's okay. As long as this letter right here, that is what we're plugging into in the function. So this, since this is I equals 2, we're plugging 2 in for I, and then 3, and then in this case we stop at 4. So what's the first term of this sequence? 5. 2 times 3 squared minus 3 is 5. Okay, and then we have 2 times 4 squared minus 3 is, and then we have 2 times 4, oh, what did I do?
You skipped one.
I did skip one. You were giving me the right numbers though, weren't you? Thank you. So 5, 29. Huh? This one's 15 right here?
Yeah.
Thank you. So this equals
40.
Quiz, would you want us to show all
on a quiz without a calculator, you wouldn't be able to just write 49 without an equal. You see what I'm saying?
that? I'm just kidding. I'll work it out.
Okay, last numeric example here. The sum from k equals the sum from k equals 1 to 3 of k times sine of k pi over 2. It looks intimidating, but don't get intimidated. We start by plugging in 1. And then we plug in 2. So 2 times pi over 2 would be pi. And then we plug in 3. Okay, flashback to some pre-calculus here. Grant, what is the sine of pi over 2?
It's 0. I had one on the paper. I didn't say it. It's 1.
It's what? You sure? Sine of pi, Jill. Sine of 3 pi over 2, Sammy. So our sum, -2. Okay, we've been working with a lot of numbers. We're going to work with a little bit more, we're going to work with more general forms now, okay? And what we're eventually going to build up to are shortcuts, okay? You talked about some shortcuts in pre-calculus. You actually used mathematical induction to prove shortcuts back in pre-calculus. And we're going to use those to help us, all right? So, first of all, you've seen this notation before in pre-calculus, but if we're talking in general, we talk about subscripts. Okay, if we talk about the sum from 1 to n of b sub k, then this is the first term, this is the second term, this is the nth term, right? So those subscripts are just telling us which term it is. Remember seeing that last year in pre-calculus, correct? Okay, so not an intimidating notation, okay? What we're going to do is we're going to talk about some properties of our sigma notation of our sums so that we can efficiently calculate some of these sums without having to use a calculator. And like I said a few seconds ago, we're eventually going to build up to some shortcuts. And so these properties are going to help us break up our sum and then use our shortcuts. Okay? So, first one. If we have a constant multiplied to our term, or to our sequence really, there's a coefficient, we can move it out in front and then find the sum before multiplying it to that coefficient. B and C you can maybe write together. Okay, B and C are basically the same concept. One is addition, one is subtraction. So if you want to switch them together or write plus or minus, you could. All right. But the second two are basically if we have addition or subtraction inside of our sum, we can split it into two separate sums that we are either, in this case, adding or in this case, subtracting. We're going to go through two examples of how we can use these, and then I'm going to show you some really awesome shortcuts. When you're finishing writing, I'll remind you it is Pep Rally's schedule today. So, we're only in here till 48. Huh? It's shorter than usual. Okay, so first example I want to talk about, the sum from k equals 1 to 3 of 2k. I'm going to show you how we can use this property.
You're just as bad as him. I don't know why you're trying to pull it off.
What we can do is we can move that 2 to the outside. And we can take the sum from 1 to 3 of k, so 1 plus 2 plus 3, and then multiply it to 2 to get the 12. Okay? I know that seems very basic right now, but once we get the shortcuts and we're doing things in general, or our sums are going to like 30, it'll be a lot more beneficial. Okay, but right now we just gotta stick with simple. Okay. Next one, write this one down. Okay. What we can do here is we can split this up to k equals 1 to 4 of k minus the sum from k equals 1 to 4 of k squared. Excuse me, k squared. Okay, so the sum from 1 to 4 of k is 1 plus 2 plus 3 plus 4 minus the sum from 1 to 4 of k squared is 1 plus 4 plus 9 plus 16. We're subtracting, correct? So the 1 minus 1, 4 minus 4 cancel. And we have 5 minus 25. I was thinking that this was 25 and I forgot about that 5. Yes. That is what I was thinking. And so I. Okay. Thank you for bearing with me. Now, what happens if we're going to go from like 1 to 30? You are not going to want to sit there and add 1 plus 2 plus 3 plus 4 plus 5 all the way to 30. Okay? So we're going to have some shortcuts. Now, I'm giving you 3 shortcuts. These shortcuts, I know for sure 2 of them you proved last year in pre-calc. The 3rd you did not. I don't know if you want to prove it or just believe me on it. Okay? But I need you to write these down. Okay, so these are our shortcuts. Do you remember the proofs that you did last year, those mathematical induction proofs? You blocked it out from your memory? Here's our first one. This is a really beneficial shortcut. I use it often. When I play cards or whatever.
It's like counting cards.
What?
Counting cards.
No, like when you know how to play rummy? You know how to play rummy? Okay. Well, you try to play like either groups of cards or straights. And so when you count up your points and you have like a straight from 3 to 8, it's a lot easier to count up your points. Huh? I don't usually have like a straight. Okay, so if you have the sum of k from 1 to n, we really could write it as n times n plus 1 over 2. Okay. The next shortcut, the sum from 1 to n of k squared, is this. It's a little bit more complicated. This is one that you'll really need to study. And then last but not least, our shortcut for k cubed, which you'll notice is very similar to that of k, and is just a square. Okay. So if you have a k squared, or a k cubed, you can use these shortcuts. Out of curiosity, what would happen this is like our example with 7. What would happen if you had the sum from 1 to n of just a constant?
So you do that n minus whatever k was on the bottom. Alright, that's added over.
How many times are we adding the constant in this case? N times. You would just take that constant times the number of times you're adding it together. Okay. Since we start at 1, it's going to be n times. Logan, I think you were thinking if we were starting at a different number. Okay. All right. So here's where it comes in handy. The sum from 1 to 23 of k. Remember, our shortcut is n times n plus 1 over 2. So what we can do here is we can say 23 times 24 all over 2, instead of having to say 1 plus 2 plus 3 plus 4 plus 5. Well, all the way to 23. Okay, Cole, did you put that in your calculator? 23 times 24 over 2?
Yes.
And?
276.
Okay. That's kind of a nice break.
Yeah.
Yeah.
Who figured that breaking out? Kepler.
It's not Kepler. I don't know if I can give you the mathematician's name off the top of my head. When we're done with notes, I'll look in our book and see if they have anything about who came up with them for you. Okay?
What's the rule called? Like, what's it called?
I don't know.
Oh, that's probably what the guy's name.
Hence why I hope. Okay? Write this one down. K equals 1 to 7 of k squared. Okay? So, what is our k squared formula? N times n plus 1 times 2n plus 1 over 6. So n is 7 times, then we have to do n plus 1, which is 8. And then what about 2n plus 1?
14.
Thank you. All over 6. Is what? I just didn't hear you.
100.
My ears are really like, cloudy.
140.
140? $140 is right. We checked Cole. Don't rely on Cole to do all your calculations.
Cole's trying to cheat grin out.
Okay, and then last on this page, sum from 1 to 6 of k cubed. Okay, remember our k cubed and k are very similar. They both have the n times n plus 1 over 2, but for k cubed we have to square that number. So we have 21 squared.
6 times 7 over 2.
441. One more before we talk about some problems in general. All right, go ahead and write this one down. Can we apply any of our rules right now?
No.
No? What are we going to have to do so that we don't have to calculate from 1 to 30? Okay, we can multiply it out. So this is really the sum from k equals 1 to 30 of k squared plus k. And then, so we can use our shortcuts, we can break this up into two summations. The summation from 1 to 30 of k squared plus the summation from 1 to 30 of k. Okay. So our k squared shortcut is n times n plus 1 times 2n plus 1 all over 6, plus our k shortcut is n times n plus 1 all over 2. With your calculator, what is our sum?
9,900.
And 20? Okay. Yes, I know that your calculator has the capability of doing this without the shortcuts, but the point is to use the shortcuts and be familiar with the shortcuts so that when we get into the bridge between this topic and antiderivatives, okay, we're eventually going to get to the point where that is not a number. Okay. It's going to be an infinite equation. It's not going to be a number. Okay, so we're going to have to use the shortcuts where that's not a number. Okay. Two more things to talk about. Okay. I want you to understand the difference between these two forms. Okay, both of these represent the sum from 1 to n of k squared. Okay, this is open form where we talk about the sum of all of the terms. Closed form is our shortcut. So you're going to have some problems where that top number is not going to be a number, it's going to be n, okay? And we're going to have to write out our shortcuts in terms of n instead of in terms of a number. And that is what our last example is going to be. So your last example, please write it down. Can we use our shortcut right now?
No.
We cannot. We need to rewrite this as the sum from k is 1 to n of 9 plus 6k plus k squared. Then in order to use our shortcuts, we can break this into the sum of 3 sums. I'm going to come back to this one with 6k. It is going to be easier if we write the 6 outside of the sum and just have the sum of k. We have the sum of a constant. From 1 to n, what's the sum of, what's that sum? 9n. We're adding 9 up n times. Okay. And then we have 6 times the sum of k from 1 to n. So that's n times n plus 1 over 2. What? We'll eventually get there. And then our k squared sum is n times n plus 1 times 2n plus 1 over 6. So yes, Cole, if you want to simplify. Well, it's easier to plug in numbers if it's simplified, don't you think? So this isn't very calculus-y, if you will. Is that a word? But I'm going to make it up. Okay. This is kind of a break. Working with summations, we'll eventually merge it together with antiderivatives and what antiderivatives mean and what we can do with antiderivatives. Okay, but for right now, we need to understand the rules and how they work. So, on your gold sheet, you have a book assignment. We have 10 minutes left in class since we have a shortened schedule with pep rally. I'd like you to use these 10 minutes to get started on your homework. Okay, the more you do now, the less you have to do on your 3-day weekend. We'll see how much we get. The storm could shift. You never know. Don't ever count on it.
No.